Okay, this is the fifth lecture for the course of quantitative and qualitative data limited variables. And today we speak about multivariate normal distribution and the matrices positive definite, and what are the conditions that we can assume when we speak about this kind of matrices. Okay, let's start from a multivariate normal. Suppose that we have a random variable x that is a vector n by 1. It's not like that. We have x1, x2, and xn. And if it is normal distributed, then we can say that x, for example, is a normal, multivariate normal with n variables inside the vector, with mean mu, where mu here is a vector, and the matrix of variance and covariance is indicated by omega, where mu we put inside mu1, that is the mean of x1, mu2, mun, and omega is a n by n matrix. This is n by 1 vector. And this omega is not like that. We have sigma 1, that is the variance of x1, sigma 1, 2, that is the covariance between x1 and x2, sigma 1, 3, sigma 1n, sigma 2, 1, sigma 2, 2, sigma 2, 3, sigma 2, n, sigma n1, sigma n2, sigma n. I want to remember that in this diagonal there are all the variances of the variables, and in all the extra elements are referring to the covariances, and this is also a symmetric matrix, because we know that the covariance of x1, x2 is equal to covariance of x2, x1. Okay. And what happens if we do a linear transformation of this vector x? We take x, we do a linear combination of these x's that is indicated by c. This is a n by 1. This is, for example, a n by n matrix. Then we say that with this kind of transformation, the normal is c mu. Then we operate or we multiplicate this matrix C on the vector of the means, and we have the covariance matrix that is like this, and this also n by n matrix. Okay, I want to remember that x, as before, is an n by 1. That is a normal mu omega. Okay, and then we can see that in this case we have c multiplied by mu, and in this case it's like to do a square in a metric sense, and then we need to pre-multiply the omega by c and post-multiply by c transpose omega, the matrix C. Okay, now we can speak about what is a matrix positive definite. Okay. All these concepts refer to square matrices. Then, for example, we have A that is m by n. Then we say that A is positive definite if x transpose AX is greater than 0 for all x different from 0. Then take, for example, a matrix A and take whatever you want. Then take a vector x, invent it, put inside the numbers that you want. Then at the end, you get something that is greater than 0. Then, if this happens, then we say that A is positive definite. And there is another definition that is m by n is positive semi-definite if x transpose AX is greater or equal than 0 for all x that you can invent. Okay, in this case, and in this case, x is a vector that is a m by 1. And then at the end, you get a scalar because this is a 1 by n, this is a m by n, and this one is a n by 1. Okay. Usually in econometrics or in some texts, we see this kind of notation, and we can say that if A is positive definite, then we say that m by n is greater than 0, and this is positive definite. And A greater or equal than 0, then is positive semi-definite. Okay. Okay, these concepts are very useful because when we do assumption on the regression analysis and we have the conditional distribution of epsilon given x, then this one is a normal, for example, with 0 and sigma. Sigma squared I. N, because this one is n by 1 vector, and this is a n by 1. This is a m by 1. This one means something like that, 0, 0, 0. Okay, now I want to show you one result, and this one says that if, for example, omega is a positive definite, then exists omega inverse. And we can express this omega inverse as a product of two matrices. And then from omega, that if omega is a positive definite, then exists its inverse, and we can find a P that is a matrix that is a m by n, such that the product of P by its transpose is equal to omega inverse. And this is a useful result when we speak about GLS estimators, because, for example, when the condition, for example, when this kind of condition is not fulfilled in our data, then we need to change the estimator, and then instead of to take this one, we take a GLS. And for this reason, this kind of result, it's very important in order to find what is the GLS estimator for a regression analysis. And with this one, we end this lecture, and see you in the next lecture.